So I promised you we'd talk about visualizing Newton's laws being applied to a whole system to better understand conservation of momentum. And I said we'd do that by focusing on a single point in the system, and we're going to focus on that point, and that is the center of the mass. So if you consider two masses in a system, so let's say a lot of mass, little mass, even though we're talking that's volume, but whatever. We would expect the center of mass for our system to lie probably closer to the heavier mass. And that distribution works for no matter how many objects we have. Perhaps we find the center of mass in between these four masses here, if that's our system. If they're all the same mass. And let me show you the way that we calculate this. So we'll start with just these four masses here. The center of mass is a position, so it's a location. And the way we find it is we take the weighted average of all the masses based on their locations. So it doesn't matter how many masses you have in your system. It could even be one mass, and all these are different chunks of that mass. But it's going to be the sum, the weighted sum of the masses over the total mass. And hopefully you can see the units will check out. So what does this have to do with Newton's laws? Well, let's take a look at when we find the total momentum of a system. Total momentum of the system will be the momentum of each object added together. And I can't stress this enough. Remember, the velocity is a vector. So let's say that we have a system that's two masses, and again we'll stick with one that's heavier than the other. Or not heavier, I should say more massive than the other. And maybe the lighter one is going slower. Yeah. So we'll place center mass right here. It should be closer to the more heavy ball. Well, if I take this equation here, I can say this is again the sum of the masses times the velocity of the system. And let me try and show you how that works, because I know that's a pretty big claim. So I can express the velocity as the rate the position changes. And so if we look here, I can divide both sides by the total mass. I left that over there. Whoops. So I'm just going to make sure I show all my steps here. But I could factor out that time. I could very well easily just kind of swap these, because it's the same time frame for both. Technical difficulty. So yeah, they're using the same time frame, so we can put them in the same denominator, or over the same denominator, and we can swap these two. Goodness, I'm making a lot of mistakes. So we can see here, this is the center of mass. So conservation of momentum can also be thought of as the velocity of the system will keep doing what it's doing as long as there isn't an external impulse. So if we revisit this, perhaps, let's get rid of this section here. So, same rectangle. This ball, let's say, has caught up to the little ball. Then hopefully it's pretty clear that our center of mass has now moved. So it's gone from here to there. And the rate at which it changes that position, that velocity represents the velocity for the whole system. So you can think of conservation of momentum as saying, or Newton's law as saying, the center of mass of the system is going to keep doing whatever it's doing unless there's an external impulse on the system. And that's all I got for you for center of mass. Thanks.